Okay, we are going to solve this second order linear homogeneous with constant coefficients using a different method. Now, this is a pretty easy DE to solve. You could probably solve that in your head right now. In fact, go ahead and solve that DE and write up what the solutions are. So, for this particular one, yeah, we probably wouldn't want to go through all this work. But this is a good method, and it's easier to teach with an easy example. This is going to be called reduction of order. We're going to convert this one single second order DE into a system of first orders by making the following substitution. Let's say U equals Y. Now we could call that, here, we'll be doing this later, so maybe we'll call this X1 equals Y, and then we'll call X2 equals Y prime. So notice, by the way, that X2 is X1 prime. Or X1 prime equals X2. That will be one of our equations. The DE itself will give us our other equation, because notice that X2 prime would be Y double prime, which we can get from here. If I move everything to the other side, that would be 8Y prime plus 15Y. But I have these guys. It's easy to get lost in the details here. I want everything in terms of X1 and X2. So at the end of the day, I want to be able to write X1 prime equals an equation that has X1s and X2s, and X2 prime similarly, equations with 1s and 2s. So this one I already have. X1 prime is X2. So I'm going to call that 0x1 plus 1 x2. X2 prime from here, because X2 prime is really just Y double prime, would be 8Y prime plus 15Y. I have names for those guys. That would be 8x2 plus 15x1. So I want to keep things in the proper order here. I'm going to call this 15x1 plus 8x2. So now we've turned this second order single DE into a system of first order DEs. And I think I have a wrong sign here. These guys should have opposite signs. I think I need a minus here, right? If I move all that to the other side. So that should be a minus. Okay. Yeah, I think we have space here. So I can write this in matrix form. My X vector prime would be the matrix 0, 1, negative 15, 8 times my vector X, where the vector X is the vector X1, X2. Okay, so we just want to find the eigenvalues of this matrix. So I want the determinant of A minus lambda I to equal 0. So let's find that here. That would be A minus lambda I would be 0 minus lambda, 1, negative 15, 8 minus lambda. I want that determinant to equal 0. So that's negative lambda times 8 minus lambda, minus, going this way, minus a negative 15, so plus 15 equals 0. If I clean this up, I get lambda squared minus 8 lambda plus 15 equals 0. Wait a minute. That's exactly the same thing we got for the characteristic polynomial if we solve this the old way. And that will always happen with these simple ones. That should not surprise us. That's this guy's characteristic polynomial. His eigenvalues are lambda equals 3 and 5. Okay, let's find both of his eigenvectors. For lambda equals 3, I like to do this version, the version that is a minus lambda I times my vector k must equal the 0 vector. So that's this guy. Plugging in lambda, -3, 1, -15, 5 times k1, k2 equals the vector 0, 0. So what do we get? -3 k1 plus k2 equals 0. Move that guy to the other side. K2 equals -3 k1, or +3 k1. So my first eigenvector, just swap coefficients, make him a 1 and him a 3. That will be the eigenvector 1, 3. And then for lambda equals 5, a minus lambda I times k must equal the 0 vector. So that would be the matrix -5, 1, -15. 8 minus 3 would be 5. Notice, by the way, of course, one row is always a scalar multiple of the other one. If that doesn't happen, you've done goofed. But that's what happened here. K1, K2 must equal 0, 0. So -5k1 plus k2 equals 0. I just took the top row. So k2 equals 5, k1. So then my vector, just swap coefficients, will be 1, 5. Okay, now I have my eigenvalues, I have my solution. So I'm going to clean all this up. I'm going to move into here where I've got some space. My solution then will be y equals, or the x vector, equals 1, 3 e to the first lambda, 3t, don't forget my c1, plus c2, the second eigenvector, 1, 5, e to the 5t. Now what we solved here was a system of differential equations, linear. I really just wanted y. That's all I was really after. So let's write out these two rows here. The top row would be x1 equals c1 e to the 3t plus c2 e to the 5t. The bottom row would be x2 is 3c1 e to the 3t plus 5c2 e to the 5t. Why do I care about those? Because x1 is y. That's what I was actually after right there. And then, so what is x2? We went through all this work. That's y prime. So if I needed y prime, there it is. But all I was really after was y. There it is. That's exactly the same solution we got when we solved this as a second order homogeneous with constant coefficients. So we're not going to get a different solution. We're going to get the same solution. In this particular case, it would have been much easier to solve it the old way. But sometimes it is easier to reduce the order instead of having to deal with, say, a second order. I could have a system of first order.